Alright, so in this video, we're going to examine the methods of fluid flow, and then later we're going to talk about it. Alright, so now we're going to examine the fluid flow of water. So next we're going to examine the fluid flow of isopropyl alcohol. So next we're going to examine the fluid flow of syrup. And now we'll examine the fluid flow of ketchup. Next experiment, we're testing water versus isopropyl alcohol. Next, we're comparing water and syrup. Next, we're comparing water versus ketchup. As you saw earlier, we just saw a bunch of fluids and their ability to resist flow, or in other words, their viscosity values. Dynamic viscosity represents a fluid's ability to resist shear stress, and it's simply just the velocity gradient over the distance it travels. The common unit for dynamic viscosity is force divided by area times time, which is also just pressure over time. And the common unit would be a Pascal per second, or in other words, a Newton per meter squared times a second, which is equal to 10 poise or 1,000 centipoise. The common way to remember a centipoise is that water's centipoise value is always going to be 1. Next up is kinematic viscosity, and it measures a fluid's ability to resist shear stress in comparison to its velocity gradient. The way you calculate it is just simply by dividing dynamic viscosity by the substance's density, and its common unit would be area divided by time. An example of this would be 1 meter squared per second, which is equal to 10,000 Stokes or 1 million centistokes. Now, Reynolds number describes a fluid's laminar or turbulent flow. Laminar flow is simply just picture like turning on your sink and you'll see water coming out clearly and you can see through it. That would be an example of laminar flow. All the particles are moving like together in like one cohesive unit. If Reynolds number is less than 2,000, you'll have laminar flow. And if it's between 2,000 and 4,000, you'll have something called transitional flow. After that, you'll have something called turbulent flow, which is when you see like white water. Reynolds number greater than 4,000 indicates turbulent flow, which is sort of seen in white water rafting, stuff like that. Or just simply just turning on your sink all the way, watching the water come down in like a white stream. It's calculated by multiplying density, velocity of this fluid, the diameter of the flow, divided by the absolute viscosity, which is, in other words, the same thing as just the velocity of the fluid times the diameter of the flow divided by kinematic viscosity. Because of this, Reynolds number will always be unitless.
All right, so for our experiment, we tested 4 types of fluids. We tested water, isopropyl alcohol, syrup, and ketchup. So the respective densities for water is 1 gram per centimeter cubed, isopropyl alcohol is 0.786 grams per centimeter cubed, syrup is 1.092 grams per centimeter cubed, and lastly ketchup is 1.33 grams per centimeter cubed. Now, each one's dynamic viscosities are measured in centipoise. For water, it's 1 centipoise. For isopropyl alcohol, it's 1.9 centipoise. For syrup, it's 150 centipoise. For ketchup, it has a range of 50,000 to 70,000 centipoise. Now, using an equation that relates kinematic viscosity to absolute viscosity and density, you get values of kinematic viscosity for water being 0.01 centimeters squared per second. For isopropyl alcohol, you get a value of 0.024 centimeters squared per second. For syrup, you get a value of 137.363 centimeters squared per second. And lastly, for ketchup, you get a range of 375.094 centimeters squared per second to 525.131 centimeters squared per second centimeters squared per second. And we should note that this larger value in range is due to the fact that ketchup is a non-Newtonian fluid, while our other 3 fluids are all Newtonian fluids, meaning that ketchup doesn't follow the same rules that these Newtonian fluids follow, Thus, these values can be a lot higher, if not infinitely larger, than a Newtonian fluid. And also noted that for kinematic viscosity, the unit centimeters squared are also equal to a stoke.
So, water ended up with the smallest kinematic viscosity value. This indicates that it has the smallest resistance to shear stress, meaning that it'll flow the easiest in comparison to alcohol, syrup, and ketchup. Ketchup, again, had the largest value, but since it's a non-Newtonian fluid, it's not generally accepted to have a Stoker or centipoise value on that fluid. Other examples of non-Newtonian fluids would be like bread dough, toothpaste, things like that. Things that can stick to something relatively easily, maybe like gum. Isopropyl alcohol was next in line. It had 0.024 stokes as its unit in kinematic viscosity, which means it was second worst at resisting shear force, meaning that it was second most readily to flow. And again, syrup was next in line with 137 stokes.
So, in terms of Reynolds number, using the equation velocity times diameter over kinematic viscosity equals Reynolds number, we find, using the kinematic viscosities found earlier, now that water has the largest RE, followed by isopropyl alcohol, and then that is followed by syrup, which has much larger value than isopropyl alcohol and water. And then the one with the smallest Reynolds value is going to be ketchup, because it's a non-Newtonian fluid. It's going to have a much, much larger value of kinematic viscosity. We're going to ketchup at last. So using these Reynolds number values, we find that water is going to be the most turbulent flow. Isopropyl will be the second most turbulent, syrup the third most turbulent, and lastly, with ketchup having the smallest Reynolds number, it's most likely to have the most laminar flow.
Alright, hello, I'm Chris, and we're talking to you about buoyancy. So buoyancy is a force that a solid feels when it's in a liquid. And the equation for buoyancy is the density of liquid times gravity times the volume of liquid. And the volume of liquid is actually the liquid that's displaced by the solid. So here in this buoyancy diagram, we have four different scenarios. Here we have block A, which is at the bottom of this tank of water. And here we see that the forces acting on block A is the buoyancy force, which goes up, and the weight of the block A that goes down. And here we have block B that is also in the tank that's fully dispensed. So here it's the same equation where the buoyancy force goes up and the weight of block B goes down. But here in block C and D, we see how the volume of liquid displaced factors differently into the buoyancy force. Because here, only part of block C is fully dispensed into the water. So the buoyancy force will actually only be this part of the water compared to the whole block of C. And everything else is the same, where the weight of the block of C is going down. And same with block D, it's just less of the volume is displaced here, and more of the solid of the block is pointing out into the air. Also, another factor of buoyancy is the force of air, where the force of air is pushing down the block, but it's also pushed down the water. So in the end, the force of air cancels each other out and is not really a factor into the buoyancy equation. So here on, let's say, example block B, we have weight of B pushing down and the buoyancy force pushing up. So here we have the buoyancy equation mentioned before, and then the weight of the block B, which would be the weight of the solid, which is equal to the mass of the solid times gravity. And since it's the only two forces acting on block B, the weight of the solid is equal to the buoyancy force. Now if we want to find the apparent weight of the solid in the liquid, we would have to do force of the solid, the weight of the solid minus the buoyancy force, because when the block goes into the liquid, it's not going to feel as heavy because there's a force pushing up instead of just one force pushing down. And so the weight apparent is going to be less than the weight of the solid. And then also one thing to point out in buoyancy is how density of liquid factor into the buoyancy force. So here we go back to this equation, the weight of the solid is equal to the buoyancy force. So then that means the weight of the solid is equal to the density of liquid times gravity times the volume displaced by a liquid. And if the weight of the solid is constant throughout, that means if the density of liquid increases, the volume of liquid would decrease because the weight of the solid is constant. And that's our lesson on buoyancy.
Hi guys, my name is Charlie Barsky, and in our first experiment we put an apple into a beaker with 600 milliliters of water. And as you can see, the apple went almost completely submerged with only about a sixth of it peeking above the water. This can be explained as our partner explained, the weight of the solid equals the buoyant force. And this can be explained through Archimedes' principle, which is buoyant force equals the density of the liquid times gravity times the volume of liquid displaced. The density of water is 1 gram per milliliter. So to calculate the buoyant force of the apple in the water, we have 1 gram per milliliter times 9.8 meters per second squared, which is the acceleration of gravity, times the volume of liquid displaced, which is the final volume minus the initial volume, which is 860 milliliters minus 600 milliliters. And then, using conversion factors, we can calculate that the buoyant force from the water on the apple is 2.55 newtons. Now, we place that same apple into 600 milliliters of corn syrup in the same beaker. As you can see, the apple floated significantly more than it did in the water. This can be attributed to the fact that the density of corn syrup is 1.48 grams per milliliter, whereas the density of water is 1.0 grams per milliliter. If we then plug that value of density into Archimedes' principle and do the calculation for buoyant force, we get the density of corn syrup times gravity times the volume of liquid displaced times conversion factors to get that the buoyant force of corn syrup on the apple is 2.61 newtons. And if we compare this value to the value calculated for the water, we see that it's extremely similar. And the only error that we see here between the 2.55 newtons versus 2.61 newtons can be attributed to the fact that the beaker that was used in the experiment did not have exact values for volume. And the reason that these are the same is because the weight of the apple is the same, which is shown as the weight of a solid equals the buoyant force when the solid is floating on top of a liquid. By using the numbers found in this experiment, we can manipulate Archimedes' principle to show the relationship between density and volume. As shown before, the buoyant force of the water on the apple is approximately equal to the buoyant force of the corn syrup on the apple. If we then plug in Archimedes' principle into each of these, we get density of water times gravity times the volume of water displaced equals the density of corn syrup times gravity times the volume of corn syrup displaced. In here, we can cross out gravity since it is on both sides of the equation. Therefore, we get the relationship of the density of water times the volume of water displaced equals the density of corn syrup times the volume of corn syrup displaced. If we then plug in the numbers and pretend that we do not know the volume of corn syrup displaced, we can solve for the volume of corn syrup displaced, which ends up being 175.7 milliliters. This is approximately equal to the value found in our experiment, which is 180 milliliters. Next, if we compare the volume of water displaced to the volume of corn syrup displaced, found by subtracting the initial volume of water in corn syrup from the final volume of water in corn syrup, we get that 260 milliliters of water was displaced and 180 milliliters of corn syrup was displaced. If we then make this into a ratio by dividing 260 milliliters by 180 milliliters, we get 1.44, which is approximately equal to the ratio of the densities of each liquid, which is 1.48 for corn syrup and 1.0 for water.